Here we have the duo drum interface. This is a flamenco box. We have a sound hole on the back. We have the beater on the front side of the drum. We've retrofitted a box, and this has an IR sensor and one switch. Its cable is being plugged into the custom Arduino box. The insides of the box, we have our Arduino Uno. We have our grounds and our analog in and digital in. We have a breadboard inside with our sensors connected. We have our switches and the sensors with plug and play cables. And on the Hungarian drum we have a similar setup in that we have a box with a switch and an IR sensor, and it's also plugged up in the same manner. Now we have our own piezo mic on the flamenco drum. This picks up the pressure levels of the physical exertion and is parsed into max MSP. In the Hungarian drum we've decided to place the piezo inside the drum because of more resonances. We have our piezo microphones being plugged into the inputs of our sound card, and that's being plugged by firewire into our computer. Here we have our Arduino inputs. They're coming from the Arduino Uno board. We've created a patch in the Arduino IDE. We're using a serial connection to send the data to Max. We've created a B patcher to house our Arduino inputs. You can see that on screen now. We're unpacking the data from the serial connection. We just have number boxes set up for our two switches and our two IR sensors. The first being the envelope follower. After the envelope follower chain, we're multiplying channel 1's envelope onto channel 1's dry sound. You can see then after that process we've set up a distortion that plugs into a spring reverb. Initially we go through an envelope follower again before we go into the distortion patch, and we send the output of the distortion to a spring reverb. We've set up of the values already. You can see the spring reverb here. We got it from the Cycling 74 forum. It was designed by Volker Baum, and it's just a simple spring reverb with a tap in and a tap out. You can just change delay time manually and gain, but for the purpose of our performance we just had it hard coded at certain values. The next part of our patch is an FFT based soft knee compressor. This just compresses the signal, and yet again it goes into the same reverb abstraction as the distortion goes into. The next area of our patch is our FM synthesis module. This reads sensor data, pressure sensor readings, and it's plugged into the patch. You can see the patch here now. We have 4 cycle tildes set up to parse the data, and we're sending that data back into our audio channel. This is the wave shifter module, which is again a B patcher like our Arduino inputs. We have our receive first and second channel coming in, which is being plugged into an envelope follower. We're then scaling the input so that it's in the range of 0 to 127. You'll see it coming into the bottom 2 sliders on the bottom of the patch. The wave shifter is basically a phase oscillation unit. Down on the bottom of the patch you will see multiply 1, 2 and 3. This is just to create minor oscillations with the original sound, which is multiplied up using cycle tildes, as you can see there, and that's being plugged into the final channel of our audio mixer. Now the audio mixer is automated with a mapping, a one-to-many mapping that we created on the Hungarian drum. You can see the custom control patch here, which handles the mapping, and It works basically, it counts the silences between presses of the switch, and in this way it allowed us to automate separate channel volume during the performance.